Okay, so let us start. So today we are going to discuss the notion of conformal vertex separated algebra. But before that, let me recall the Kac-Moody vertex separated algebra we discussed last time. So recall that we've started with the simple Lie algebra G, and then we have the corresponding affine Kac-Moody Lie algebra, which is G tensor CTT inverse, and plus CK. So this is the central extension of our algebra, and we have a killing form, and the bracket is given by y ti delta I plus g 0 I k x y. So here xy is the killing form, and this is the definition of the Kac-Moody Lie algebra. Fine. And inside we have a subalgebra that is denoted by gt, which is nothing but g tensor c of t. And obviously this is the subalgebra inside g hat. Okay, so we see that the bracket does not contain anything of this form. So this works. And so given the subalgebra and the corresponding Kac-Moody Lie algebra, we have the so-called parabolic Fermat module or induced module. Induced module. So this is the following. So we fix a number k, which is an arbitrary complex number, and we consider vk, which is the module induced from gt plus ck. So g hat. Here we have one-dimensional module corresponding to this number k, where this k acts by constant k and gt acts together. So in other words, so vk is isomorphic to the universal enveloping algebra of g tensor t inverse ct inverse as a vector space. Okay. So this is our vector space, and obviously, money, and obviously vk is graded. So vk of n, where n counts the degree of t. So for example, so what is the dimension of vk0? Well, it depends on what do you mean by counting the degree of t. So let me put, in order to make it absolutely clear, let me put t inverse here. Mhm. Well, it's not really important, of course. No, it's one, just one. Yes, because so this is the vk0 is just the span of the vector of just ck itself. So it's the span of say vk, where let me say that this ck is c times vk. Okay. Does this make sense? Okay, and what is dimension of vk1? G. Yeah, this now is right. Yes, dimension of G. So just because this space is spanned by the elements of the form x tensor t inverse. Yes. And just to make it absolutely clear, so what is the dimension of vk of 2? Yeah, but can we give it explicit description? So is it okay? Any other suggestions? Actually, it's almost true, but not exact. Uh, yes. So now. Mm-hmm. That's true, but still, I don't like the answer. Again, it's even closer, but what should we get if dimension of G is 1? Of course, so G, there's no simple algebra of dimension 1, but just assume that we have a one-dimensional thing. No, we don't have it. Yeah, we have only negative units. But once again, so what would you, could you please tell me what should be the answer for dimension of G equals 1? So please make up your opinion and raise your hand so I can see it if you have such an opinion. Why? Yes, it's true. Why? Mm-hmm. Great. But what do we have here? Yes, so how to fix it?
So the second summand is with t minus 2.
Right.
And with the rest is
So probably should be the
plus 1.
Because we can have some repeating elements.
Sure. Yeah, because the universal Novel algebra behaves like a symmetric algebra, right? It's not the kind of skew symmetric algebra, symmetric algebra. So therefore, so you can't have repetitions. Therefore, you have this plus one. Okay. So any questions so far? Okay. So this is our space, and so maybe I put a remark here. Vk is naturally a G-hat module. Just by the very definition. So of course we have this very explicit description as a vector space. However, the initial definition is the induction from somewhere to G-hat. So therefore G-hat acts on the space, and it's important to keep this in mind. Okay, so now the claim is that so there is a so Vk is vertex separator algebra. Well, I mean, even more concretely with the vacuum being Vk and y of J A, let me put it like x tensor T inverse of Z equals to some x T to n Z minus n minus 1 for any x from G. Okay, so if we take x from G and then we tensor it with T inverse, so I better put Vk here. Yeah, so this is an element from the affine Lie algebra, and then since Vk is a module, we can apply this operator to Vk, getting another element, and then we consider our vertex operator corresponding to this vector, and this is the result. We can give even more concrete description, namely, so let J1 up to Jn be a basis of G, and then we have the following formula: Ja1 minus n1, As minus ns, 0, Z is 1 over n1 minus 1 factorial, and s minus 1 factorial. And here we have the normal ordering of the derivatives. D is 1, Ja1. Like this. And actually, this comes from the general reconstruction theorem we had last time. Okay. Good. So, any questions about this Kac-Moody vertex operator algebra? Okay. So if not, let's go ahead. Today, how many people are in Zoom? 3 students. Okay, so then I encourage people in Zoom to ask questions. So as usual, your active participation is highly appreciated.
А вы нас слышите?
Yes, yes, we can hear you.
Хорошо.
Okay. So our next example is the Virasoro algebra, Virasoro vertex operator algebra. So please note that even, well, I mean, we already have several quite non-trivial examples. Well, actually, 2 examples, Heisenberg and Kac-Moody. And in both cases, we are starting with the Lie algebra, infinite dimensional, but Lie algebra. And then we proceed with vertex operator algebra, which is a more complicated object. However, the starting point is the Lie algebra. So it's not really necessary. So in principle, one can have vertex operator algebra not based on a Lie algebra. However, our first examples are of this sort. So let us continue in the same direction. So most of you probably know what is the Virasoro algebra, but let me recall that. So Virasoro Lie algebra is well, more or less based on the vector space CTT inverse dt. So these are derivations of the ring of polynomials in TT inverse. And well, there is a basis here, Ln, which is minus t to n plus 1 dt. So the minus is for convenience, and this n plus 1 here is to make the total degree to be equal to n. So let me put here corresponds to, so it's not really equal, but so first of all, let's compute what is minus t to n plus 1 dt and minus t to m plus 1 dt. So please raise your hand if you know what's the answer. Okay, then let's spend half a minute to compute. So I wrote down the formula. So does it agree with your computation? Yes. Very good. So then we can rewrite it in terms of ln and lm, saying that this is n minus m ln plus m, and this is the so-called Witt algebra. However, to get the Virasoro algebra, you have to extend it, adding one-dimensional central extension. Well, which is the this one-dimensional space is spanned by an element C, and then we have here n delta n plus m 0 and n cubed minus n over 12. Okay, so yeah. Oh, sorry. Thank you. Yes. So our Virasoro algebra is, after all, this CTT inverse dt plus one-dimensional central extension. So this is the algebra, and so now let us organize, maybe one lemma. So let us denote by their derivation of O. So we'll see in a minute what does this mean. So just the span of Ln with n greater or equal than minus 1. Okay. So you see, if n greater or equal than minus 1, then this power of t is non-negative, and therefore these can be seen as derivations of the polynomial ring. So O here is polynomial ring, and so then the subspace is the subalgebra, the Lie subalgebra. Okay. So it's easy to check. So the only non-trivial thing is that you have here inside L1 and L minus 1, but you see that if n is 1, then this cancels. Therefore, you don't have central extension if you compute a commutator of two elements from this subalgebra. So it's indeed a subalgebra. Okay. Now, so we want to organize the following series: C of C, the sum Ln z to minus n minus 2, and from Z. So the reason for this minus 2 is actually will become clear a bit later, but just why this is really the right way to write, because you see here the subalgebra starts from n greater or equal than minus 1, and if we compare it with the Kac-Moody case, yes, in this Kac-Moody case, our subalgebra was GT, which starts from 0. And this is more or less the explanation why do we need such a shift. But we'll see later why this is really kind of natural. So far, this is a series with coefficients in our Lie algebra. And then, of course, since we are doing the vertex separated algebra business, so we want to organize the vertex separated algebra from this. And first of all, of course, we have to check the locality. Yes, I should have said here, of course, we've discussed it last time, but let me write a formula here. So why do our formulas make sense? And the reason is that we can compute GA of Z, the commutator GB of W. So do you remember what power of Z minus W do we need to take in order to annihilate this commutator? Yes. And I think we did this computation last time, did we? So hopefully yes. And then, so one wants to mimic the same thing here. And so let me put it as a lemma, saying that if we take T of Z, T of W, and we take the commutator of these two fields, then they are local. And actually, the power one needs is 4. It's equal to 0. So we are not going to give the complete proof. So I think I'll leave it for you as a homework, but let me just write what do we need to check. So we need to check that sum L n Z2 minus n minus 2, and then the sum Lm W minus m minus 2. So this should be 0. And then we know what is Ln, Lm, to the 4. And here we have sum and m, Z2 minus n minus 2, W minus m minus 2. And n minus m, L n plus m, plus this central element n cubed minus n over 12, delta n minus m. That's it. So you multiply it by Z minus W to the 4, and then you need to check that it's 0. So there are two terms, and well, just check. Okay. So homework. And now, so let me repeat once again that this is the formula which holds true in the universal enveloping of the Virasoro-Lie algebra. So we don't need a vector space here. So this is not about the action of the algebra, but this is about the operators themselves. Yeah? Okay. But in order to organize the vertex separated algebra, we need a vector space, right? And for that, let us mimic the construction we had in the Kac-Moody case. So namely, so let us fix a complex number C from C, and consider the module for the Virasoro algebra, which is defined as the induced module from the subalgebra where O plus C times C. Okay. So this is the induced module to the Virasoro-Lie algebra. And we have our subalgebra, which is, you remember, the subalgebra somehow starts with L minus 1 and then goes with L minus 0, L1, and so on. Very good. Now, let's try to somehow, yes, I should have completed it first. So this is C times C. Yes, this means that this der O acts trivially, and this capital C acts by a small c, by the number. So this space is graded. And we say that again, let's say that V sub C is our one-dimensional space. And so we have this direct sum decomposition with the keeping in mind that the degree of L k is minus k. So please note that as a vector space, our Virasoro module is isomorphic to the universal enveloping algebra of the span L less or equal than minus 2. Okay. So let us do the same computation as we did for the Gauss-Moody case. So please let me know what is the dimension of Virasoro C of 0.
One.
It's 1. And then dimension of Virasoro C of 1.
0.
Okay, so this one suggestion. Any other suggestions? So is it clear why this is 0? Okay. And what about the dimension of Virasoro C1? Why? What is the dimension?
1.
Yes. And if I put 3 here? Sorry?
Two.
Options, 1 or 2. So any other suggestions? And then we can vote.
Oh no, it's 1, sorry.
Sorry?
It's 1.
Okay, so 2 votes for 1 and 1 vote for 2. So what about other votes? Okay. So 3 votes here and 1 vote here. So Slava, what do you think? Irina, what's your opinion? There's one more option. 1 vote for that. Angelina, what do you think? Wow, we need your vote.
There is only L minus 3, so 1.
So, so we have our, where did I write it? So I wrote it here, yes. So the only way we can get there is acting by -3. So this is the dimension of the span L minus 3 B. And therefore this is 1. But if we go further, the dimension would grow. For example, here we have L minus 4 or L minus 2 squared. Yes, so this is already 2. And so on. Okay, so now one more remark, which is kind of obvious, says that the space has a basis of the form L minus n1, L minus n2, and S by 2dc. So here n1 is, say, greater or equal than n2, and S greater or equal than 2. Oops. And you see, this is actually the reason for the shift we have for our T of Z, because so the operators we are applying, they start with -2 and then go down. And then we put forward the following proposition. So we have a structure of VOA on our vector space with the following properties. The vacuum is our vector VC, and Y of L minus 2, 0, Z is T of Z. So you see this vector actually is of degree 2. So L minus 2 of Z is of degree 2, the only vector. And this is the field T of Z, which corresponds to this vector. So you see now this T of Z is not the formal series as we had there, but actually the series whose coefficients are operators on our VRC. Yes, so this is now understood as an element in end VRC of ZZ inverse. Okay. And we also need the general formula, which says that Y of L minus N1 and S 0 Z is 1 over N1 minus 2 factorial and S minus 2 factorial. Please note these two. And here we have the normal ordering of dz and 1 minus 2 T of Z, dz and S minus 2 T of Z. So, Again, this is the reconstruction theorem. Since we know that the field T is local with itself, so our vector space has a basis of the form there. And once again, keeping in mind that we have the correct shift here by 2, or labeling starts with 2. So this is the form of the reconstruction theory. So you might ask, why do we care about this Virasoro algebra from one point of view? So this is just an interesting example. From the other point of view, this Virasoro algebra shows up everywhere, and we'll see it in many examples. So this is not only just because of curiosity, but also because they somehow God-given. Okay. So any question about the Virasoro algebra? So if you don't have questions, I do have. So what is the operator T? So you remember in the definition of the vertex operator algebra, we had an operator T implemented into the definition. So we need this T here. So any suggestions? So this should be an operator acting on our vector space, VRC. And we need some expression for this. So do you remember the definition of T? No, it's a definition. No, it's a definition. It is. So actually, I think it's how we define it. No. So actually, definition. Let me check, but I think it's exactly how we formulated it. There are several ways. You're right, but I think this is. Yeah. So we did actually to be more precise. What we said is that y of a z, but indeed, if we can prove this one, since our formulas are expressed in terms of derivatives of t, then it's enough. So do you know such an operator?
Probably it's L1 or L minus 1.
Okay, let's make a choice. Yeah, and also we need, of course, that, so this one, there's another thing to check is that t applied to 0 should be 0. T applied to the vacuum should be 0.
Between L minus 1 and L1, we should take L1. I'm sorry.
Both are fine, yes? So actually it's important to think that both L1 and L minus 1 act trivially on the vacuum. So we have to look here. So what is the correct?
It seems to be L minus 1.
So since this turned out to be a problem, so let us make a computation. So we can compute L minus 1 with the sum L n z minus n minus 2. So what is that? Well, L minus 1 does not have the central part in the commutator with anything when you take the commutator, because L minus 1 with L1 gives n cubed minus n, which n is 1, so it vanishes. Therefore, this is the sum over n. Minus 1 minus 1 minus n. Okay. And then we have here ln plus 1. Oh, minus 1. Z minus n minus 2. Okay. And this is nothing but dz sum ln minus 1 z to minus n minus 1, which is dz cubed. Okay. So the interesting thing is that the operator somehow can be expressed via the Virasoro generators very explicitly, namely it's just one of the generators, L minus. Good. Yes. By the way, we should have also done the computation in the Kazmudy case. So what is the T for the Kazmudy algebra? How to compute it? We might not be able to give such an explicit description, but at least how to compute T for Kazmudy. So we know that T applied to the vacuum should be 0. One, 0. How should I proceed?
Взять коммутатор.
Yeah, it's a good idea. So we better have an expression for such a commutator. So what should it be? The shift.
I mean, what was the power of that?
Minus 1. Mm-hmm. Is it correct formula? So once again, remember, what do we need? Say it again. Is this formula correct? I disagree. Please. Make a computation. Okay, so it's the again. So let's compute, and so we have plus minus here, two variables, and also we have two options here.
For first n should be minus. I'm sorry, it's minus plus.
You prefer minus? Let's skip two options still. And what about this?
So if below we have minus
We have minus there. No, then it's plus. No, it's plus.
Here.
Here it's plus.
Yes. And
Okay.
then it will be plus on the right.
Minus n minus 1.
Okay, so two votes for minus one,
What's so hard?
one vote for plus one. Angelina, what is your opinion? And what about the audience from Zoom? So what do you think? They how many?
Troubles.
One? And then how many people do you have in Zoom now? Two students. Okay. Okay, so this is the correct formula, and actually you see that this minus one is kind of important because so the commutator here should give us the derivative. So you can see that when we take the derivative of something, yes, so we make this power smaller. Yeah, it means that if you want somehow to compute what's really happening, you need to make the degree so this number also smaller. So, well, of course, before unless you compute it, so this kind of does not look absolutely evident, but the degree of the operator t is always 1. So it somehow kills the vacuum vector, but otherwise it somehow makes the degree 1 larger. So you can keep in mind such a picture, and then t somehow moves inside the vector space. Okay. So that's it. Yes? Sure. Sure. So the formula looks like A1 minus N1, JAS minus NS vacuum is then the sum. So we consider the commutators. and some ranges from 1 to s. And we have n I, a I, minus n I, minus 1, and okay, so you just start commuting t with everything, and then at each stage you have a commutator, which we know. Thank you. Yeah. Yeah. So I mean, this guy equals to the commutator, and so then, yeah.
I'm sorry, but I thought about this formula like t in terms of j a1.
This is also possible. We'll get there. We'll get there. So this comes from the so-called Siegel-Sugawara construction, and it does exist. But I mean, if you want just to compute it, then it's well, so any questions about the Virasoro algebra? Okay, so if not, let us give the general definition of what is called the conformal vertex separated algebra, V. So by definition, this is a vertex separated algebra. So V is a vertex separated algebra equipped with a fixed vector omega from V2. So let me write that V is a direct sum Vn, n from Z. And let me write is a Z graded vertex separated algebra. So we have this vector omega such that first of all, okay, maybe it's not a condition, but a notation with y of omega z being the sum omega n z minus n minus 2. So this y should be series with coefficients being endomorphisms of v. So each omega n is an operator on v. Okay. So such that first of all omega minus 1 is t. So you remember we have an operator t acting on our vector space, and this should come from this omega. And then omega 0 restricted to Vn should be just n times identity. And the last thing is that omega n satisfy the Virasoro relations. So meaning that omega n omega m is n minus m ln plus m plus delta n plus m 0 times n cubed minus n over 12 times c. Thank you. Thank you. And this C is some constant, and the constant C is called the central charge of V. Okay, so we need our V, our vector space. We need a vector omega from V2, and we need some conditions on the vertex operator corresponding to this vector.
Sorry, do
Yep.
these conditions find them in any order? Can there be two different orders?
Yes. Inside the same vertex operator algebra. Yes. So we'll see an example in a minute. However, in our example, the charges are going to be different. So I don't know, maybe there are some examples of, I think there are some examples of different omegas with even the same central charge. So of course, this omega is not unique by any means. One remark about the notation. So you remember our general convention was that y of omega z is the sum omega n z minus n minus 1. Okay, so this is the general pattern how we denoted the vertex operators. And so by our definition, this, well, just let's rescale it, saying that it's z minus n minus 2, and we put here n plus 1. Okay, so I just shifted n by 1, and therefore omega n plus 1 in brackets equals to omega n. Okay, so this is the difference which one should keep in mind, that if you work with the Virasoro algebra, then there is a shift in the indexing of our basis vectors in the Virasoro algebra due to the fact that we always are working with the subalgebra starting with minus 1. Okay, so now let's see some examples. So the first example is V being the Virasoro algebra itself. I mean, not the Virasoro algebra, but the Virasoro vertex operator algebra attached to the module Vir C. So what should be omega here?
L minus 2 on vacuum.
So any objections, suggestions, comments, remarks?
Maybe we exclude something like omega 0 and central charge is not the same as morphism for our C our vertex operator algebra.
Yes. So we don't have to exclude. Yeah, absolutely. So we'll see. We'll say this. So actually, let me write it. But so any comments or questions? Just by definition, right? So that's how we define it. So important remark actually, which Andrei made. So we can. So in other words, so we are looking for, or we are interested in morphisms from vertex separator algebra morphisms from Vir C to V with the, well, I mean, this is not an obvious claim. So I mean, the morphisms of vertex separator algebras is something more than commutative relations for an operator. Yes, vertex operator. So it's not actually clear whether this is the same thing, but actually it is. So. Okay, so this is for Virasoro, and let us consider one more example. So let's get back to the Heisenberg vertex separator algebra. So vertex separator algebra. So it is, you remember, so as a vector space, V is just a Fock module pi. So there's a Fock module, and then so as a vector space, pi is isomorphic to polynomial ring in h minus 1, h minus 2, and so on. And then, so can you tell me what is the pi of 2? So where should we try to find our vector omega? So let me make one thing. So please raise your hand if you know what's the dimension of pi 2. Okay. Slava, what's the dimension? Yes, it is. Because of this span of h minus 1 squared and h minus 2, right? So let us write omega as h minus 1 squared plus some lambda times h minus 2. So this is the general form, almost the general form of a vector there, up to h minus 1 squared. So let's see if it works. So could you please tell us what is the vertex separator corresponding to such an omega? Maybe I put a lambda here. Just by definition, what should it be?
Ordering of each set.
Normal ordering.
Normal ordering of each set.
Very good. So this is our operator, and let me write this as we did before. This is the sum omega lambda n z minus n minus 2. Okay. So let's try to see if it somehow is fine for us. So let me do it here. So first of all, let us check what is omega lambda omega lambda 0. So can you tell me what is that? So please remember that h of z is the sum hn z minus n minus 1. So we need to check that omega lambda 0 is in fact the operator which somehow computes the gradient of the vector. So let's write an explicit formula for this. So just can we extract the coefficient in front of z minus 2 from here?
Plus sum.
So we have the sum over, can I write it in this way? H n h minus n. Is it okay? And also we have some term from here, which is where should be minus? Minus. Well, you're right, but you remember it doesn't really make difference because so here we made a convention that h naught x treated. It's not really important, but in principle you're right, but it's not really important. Yeah. So we can have the minus here, whatever. So because it's just h naught x is a constant, yes, and this constant does not make any change, so this actually goes to 0. Okay, and what about this? How does it act? Well, we need to understand how does it act on a vector. Oh, maybe I should put 1/2 here to make it correct.
Greater.
So we want actually to understand that if we restrict it to pi k, this gives us k times identity. So is it true? So remember that this our space is just such a ring. So what? How to write this operator as an operator on this ring?
Let's see about this A and H, say minus A. And we see that it's like proportional minus A with Vertex and A.
So first of all, do you agree with such a formula? But h0 x trivial. So
I need not greater but less. Negative part.
we need positive part on the right. So you see, the idea is that you first try to kill the vector, and then because you want finite sum after all.
Yes.
So if we had here first negative, then you go deep and then get back, but we don't want this. Okay, so how does this operator is written as an operator on the polynomial ring?
n d по dh minus n.
Yeah, so this sum n greater than 0. So this h minus n is just h minus n. And then we have n d over dh minus n. Okay. So h minus n is just the element here. And the h with positive n is just the derivative times the n. And you see this is a very nice Euler vector field, whatever it's called. So I mean, it somehow differentiates, gets this back, and then you have this n, which somehow is responsible to this. So this is somehow clear. Okay.
So I think that all omega is well connected with
Conformal vectors. Yes, yes, yes. That's right. Okay. Now, now, so let's write what is omega lambda minus 1. So can you give me the formula?
minus n plus 1.
Like this? I think we don't have anything from lambda because if n is minus 1, then this z is z inverse.
Okay, yes.
And we have no derivative coming to. Well, and this guy is nothing but the sum over n greater than 0, hn, h minus n minus 1. Okay. Well, and then clearly omega lambda minus 1 at vacuum is 0 because we act with positive first. And then another thing to check is that sum h minus n minus 1 hn, if you commute it with h of z, what you get is d z h of z. And actually, this is an explicit computation, which is easy to do. And what is more important, let me put forward the following lemma, saying that if you take omega lambda n and then commute it with omega lambda m, then the result is n minus m, omega lambda n plus m, plus delta n plus n 0 times n cubed minus n over 12 times 1 minus 12 lambda squared. And this is something to check. Not too complicated, but still. So I leave a proof, the homework. But the conclusion is that any such an omega produces a conformal structure. So gives us the structure of conformal vertex operator algebra on the Fock module as we wanted. And now this is the Heisenberg algebra structure. So you see that actually this another evidence of the fact I mentioned that the Virasoro algebra is somehow everywhere. For example, here it shows up just as a kind of miracle, because so well you take any more or less any vector from the second degree part, and then these operators satisfy the Virasoro relations. I mean, why? Okay, and now we have several more minutes. Let me mention the construction of the so-called Siegel-Sugawara vector. So this is the Kac-Moody setting. So let me take JA to be the basis of G, and J down with lower index A to be the dual basis of G with respect to the Killing form. Then I denote by S the vector sum A from 1 to dimension of G, J A minus 1, J lower A minus 1 applied to the vacuum, and this sits in VK. Do I need a half here? Yes, I do need a half. Okay, so is it clear what is this vector? So this is a vector on the second of degree 2. So from degree 2 part of our vertex operator algebra. And then, so I take the sum over indices from my Lie algebra, and then I take the GA minus 1, so meaning tensor T inverse, and also G lower A tensor T inverse, and then I form this Siegel-Sugawara vector, and the theorem says that, yeah, maybe I should also first say a remark that S does not depend on the choice of JA. Yeah, so the second basis is just a dual basis, so it's determined by the choice of the first basis. However, this S does not depend. So I mean, this is a general feature. So I mean, if you change the basis, change the dual one, then such a product somehow is not changed. Well, it's general linear algebra claim. Okay, and then the theorem says that then if you take S over K plus check, so this is the conformal vector for VK, where H is the dual Cox number of G. So this means that dual Cox number means that, for example, H hat is N for S11. Okay. So in other words, we can make it explicit. So I mean, we say that y of s over k plus h z is 1 over 2k plus h, and then the sum a from 1 to dimension of g. And here we put j a of z, j lower a of z. And this should be the sum omega n z minus n minus 2. And here we put n from z. Yes, and these omegas, they should satisfy, they do satisfy the Virasoro relations. And this is our conformal structure. Yes, I also have to say that the central charge is k times dimension of g over k plus h. Good. So I think that's it for today. So before I stop and you ask the question, so let me say that next Tuesday, we'll have a midterm exam. So this is going to be an oral exam. So we'll talk with you based on your solutions of your homeworks and of the large homework from the previous time and other homeworks. And so this is going to be in person here. But again, if you can't come, but you want to pass the midterm exam, please contact me and then we'll arrange the time. So I'll write this announcement on the web page of the class, but please keep this in mind. Okay, any questions?
Hopefully answers the question about two different conformal structures, the same central charge.
You also. Mhm. That's right. So further questions, comments? Okay, if not, let's stop for today and then next time we'll